Hi everyone, Dr. Burns here with our next chapter on electrochemistry. We're kind of going to be switching gears in this chapter where we are no longer going to be talking about equilibrium anymore. However, we are still going to be exploring reactions that we've talked about generally in General Chemistry 1, but now exploring in more detail here in General Chemistry 2. So the electrochemistry chapter has to do with the transfer of electrons in chemical reactions, which, if you recall from General Chemistry 1, was referred to as a redox reaction. If you haven't already, please make sure you go back and watch our review videos on redox reactions as well as oxidation numbers. Some students may have not gotten oxidation numbers in their General Chemistry 1 curriculum, where some students may have, depending on when you took it and what our curriculum looked like at the time. Regardless of when you took your general chemistry course, and if you learned about oxidation numbers or not, it's always good to go through that kind of review just to refresh your mind now that we are going to be talking about it here in this chapter many months after we've talked about it in General Chemistry 1. So please make sure you go back and watch those review videos just so you are prepared to go even more in depth in this chapter. So when we've talked about redox reactions, we have to consider balancing them. So a redox reaction is one in which there are changes in oxidation states, or the oxidation number, for each individual element that is participating in that chemical reaction. So we see here how certain oxidation numbers have changed from the reactant side to the product side. For example, carbon went from a -4 to a +4. Oxygen went from a 0 to a -2 and a -2. The only one that didn't change oxidation state is hydrogen, where it went from a +1 and stayed a +1 in both sides of this reaction. The same can be said with our reaction between tin and copper. So tin went from a 0 oxidation state to a +2 oxidation state, and copper went from a +2 oxidation state to a 0 oxidation state. We have to remember that that change in oxidation state is because of the transfer of electrons. Where are the electrons going? Again, we're switching gears from what we talked about in previous chapters. When we were talking about acids and bases, we were talking about the transfer of protons or hydrogen ions, whereas here we're now talking about a change in the electrons, or a transfer in the electrons, so a change in charges. Okay, so we're switching what we think about here in these types of reactions. So all redox reactions can be thought of as having two halves. One half produces electrons, which we refer to as the oxidation half. When we're producing electrons in oxidation, we would expect to see the electrons on the product side, because a product of that reaction is the production of electrons, or the transfer of electrons from a reactant to something else. The other half requires electrons, so it accepts the electrons, and this is referred to as the reduction half of the reaction. So here we would see electrons on the reactant side. They're accepting the electrons into their reaction, into that specific element, therefore it is going to be a reactant in the reduction half reactions. Now when we're talking about these halves, we're going to show each reaction, the oxidation and the reduction half, in half reactions, which we've talked about previously in General Chemistry 1, writing out those half reactions. So the electrons that we talk about being on the reactant side and the product side are only going to occur in those half reactions, in those individual half reactions. When we write the overall reaction, we are not going to see any electrons on either side of the arrow because we're going to have charge balance. So the number of electrons that are transferred from the oxidation half will be the number of electrons that are accepted by the reduction half. Another quick reminder of how we think about redox reactions is our mnemonic devices that we can use to remember where our electrons are going in oxidation and reduction. So we have two that we've talked about, or that you may have heard about in General Chemistry 1 and in our review. First is oil rig. And then there's Leo, the lion goes grr. Leo and grr. So those stand for oxidation is loss, reduction is gain. Okay, and if you do Leo, the lion goes grr, that's lose electrons, oxidation, and gain electrons, reduction. So, just ways to remind yourself where the electrons are going, if they're being lost, if they're being gained, and where you would expect to see them in your chemical reactions. So let's take a second and practice writing out the half reactions for two redox reactions here. So our first reaction is Na, sodium, plus Cl, chlorine, produces sodium ion and chloride ion. So remember, when we're writing out our half reactions, the half reactions are just showing what changes are happening to a specific element or compound. So a half reaction wouldn't be chlorine turning into sodium. We can't physically change our element in a half reaction. That would not balance out correctly. So we just have to track where each element or compound is going or turning into. So sodium turns into sodium ion, and chlorine turns into chloride ion. So our half reaction would be Na turns to Na plus, and Cl2 turns into Cl minus. So we show what each element or compound turns into from the reactant side to the product side, because what we can then do is start to balance those equations both with stoichiometric factors as well as with electrons to see where the electrons lie, to know if it's going to be an oxidation or a reduction half reaction. So we can see here that these two reactions are not balanced, both charge balance and mole value balanced. So the sodium here, we have sodium turning into sodium 1+, so we don't have charge balance. We have a charge of 0 on the reactant side and a charge of +1 on the product side. So we want to balance that out using electrons. And remember, an electron we show as E-. We can always add multiples of those so that we can have multiple of that charge. So if we wanted our two sides of our arrow to be equal to each other, which side do you think that we need to add the electron to in order to balance the charge out? It would be the product side. So we would add 1 electron here so that we would end up with a -1 charge. +1 and -1 cancel out to 0, therefore we have an overall charge on this side, on the product side, of 0, and on the reactant side also being 0. If we look at our chlorine, we have Cl2 turning into Cl-. Well, that's first not balanced in the number of moles, so we know that we need to put a 2 in front of that chloride ion in order to have the balanced number of chlorines. But now if we look at our charges, we have a 0 charge on the reactant side and a 2- charge on the product side. Remember, since we have 2 chlorines, that 2 is going to apply twice to that negative charge. So I have 2 negative chlorine ions, so my overall charge on my product side is 2 minus. So if we wanted to add electrons to one side of that reaction, what side would we have to put it on in order to balance the charge? This one would be the reactant side. We would have to add our electron to the reactant side, and we would also have to add 2 of them, so that we ended up with a charge of 2 minus on the reactant side to balance out the charge of 2 minus on the product side. Remember, charge balance does not always mean 0 on either side of the reaction. Since in our redox reactions we can only show electrons, we can only add in electrons to our half reaction, that may mean that we either have to balance out a positive charge with an electron or balance out a negative charge with more electrons on the opposite side. So charge balance does not mean 0 on both sides, it just means the same charge on either side. So, if we look at these 2 half reactions, we can now identify which one is the oxidation and which one is the reduction half reaction. So remember, oxidation is the loss of electrons. Loss electrons, oxidation. So, if we were losing electrons, we would see the electrons in the product side. Since sodium has the electrons in the product side, this would be the oxidation half reaction. Whereas the chlorine, the electrons are on the reactant side, meaning they have to accept or gain those electrons in order to get to the product. Therefore, gain electrons is reduction, or reduction is gain. So this would be the reduction half reaction. Now, in order to finish off a oxidation reduction reaction problem, a redox problem like this, we have to add our 2 half reactions together to get our completely balanced chemical equation to show the redox. So if we look here, we have sodium creates sodium ion and 1 electron, whereas the chlorine needed 2 electrons to add and create the 2 chlorine ions. So our number of electrons that were transferred in this chemical reaction are not equal. So what we have to do is multiply our first equation by a factor of 2 in order to show that the electrons are equal to each other. The number of electrons that are lost must be equal to the number of electrons that are gained. We oftentimes show this as Leo must equal Ger. The loss of electrons must equal the gain in electrons. So, if we were to add these 2 up, well, that would mean that 2 electrons and 2 electrons would cancel out, just like we saw in Hess's law when we started multiplying and adding things up, things cancel. We would then end up with 2 Na plus Cl2 combines to form 2 Na plus 2 Cl minus. And now we have a fully balanced chemical equation that is balanced not only in the number of moles or molecules on either side of the arrow, but also balanced in the charges. For our next reaction that we have here, we're going to write out the half reactions. And again, we just want to track where or how the individual element or compound is changing in the chemical reaction. So we can see here that SO3 is turning into SO4, right? The sulfur is, the sulfite is turning into sulfate. And then the manganese is turning into Mn2+. So we see here how the individual compounds or elements are changing from one side of the reaction to the other. So our first half reaction can be written as SO3, 2 minus, turns into SO4, 2 minus. And our second reaction, MnO4 minus, turns into Mn, 2 plus. Now you can see here from those two half reactions, it's not as easy as our previous example to start balancing those with electrons or anything else, because we now have these other elements that are changing, right? We have oxygens that are going from O3 to O4. In our second reaction, we have an O4 that just disappears on the other side of the reaction. And those aren't necessarily part of those half reactions as of right now. But as you can see from our reaction, our original reaction, we have this water and this H plus that aren't part of those half reactions right now. We can't have a third half reaction where H plus turns into H2O. There's no third half reaction that would lead to 1.5 reactions, which we can't have. So what we're going to see in the rest of this reaction is, or rest of this lecture, is that for more complex redox reactions, hydrogen ions and water are going to help us balance. So they're going to be tools that we can use to help us balance these more complex redox reactions, where we're not just changing the number of electrons on a specific compound or element, but we're actually changing the number of individual elements in that compound. So let's start exploring that. So when we're balancing chemical or complex redox reactions in our aqueous solutions, the key is the number of electrons produced must be the same as those required. So this is again where LEO, the number of electrons that are lost, must equal the number of electrons that are gained, GR. So LEO must equal GR. So we're going to look at balancing these complex redox reactions in two different solutions. First are going to be acidic solutions, where we have some hydrogen ions present, and the other type is going to be basic solutions, where we have hydroxide ions that we need to utilize. Okay, we're not doing acid-base reactions here, we're just using the fact that H plus means acidic and OH minus means basic to help us balance these chemical reactions, these complex reactions. So for reactions in acidic solutions, we need to utilize a 7-step procedure in order to balance that redox reaction. Okay, it seems like a lot, but it's just so that we take our time and make sure that everything in those half reactions is properly balanced for both elements and charge. So we'll start off with balancing in acidic reactions or acidic solutions, because when we get to basic solutions, when we want to start balancing in basic solutions, we're still going to utilize the 7-step procedure that we used for our acidic solutions, but we're going to add 2 additional steps at the very end. So we're going to start off those reactions in basic solutions. We're going to start them off the same way. We're just going to add 2 extra pieces at the very end to account for the fact that this is a basic solution. Okay, so the best thing that we can do for learning these complex balancing reactions is to just go through the practice. So let's go through our 7 steps first, and then we will use those 7 steps to start balancing those reactions. So when we have redox reactions in acidic solutions, the steps in order to balance them are as follows. The first thing that you want to do is write the separate half reactions. So just like we were writing the half reactions in our previous 2 examples, look to where each compound or element is turning into from the reactant to the product side. And as we saw in our second example, we're going to ignore hydrogens and waters there, because we now know that those are actually going to be tools that we can use to balance those reactions. So our next step after we've separated those half reactions is, for each half reaction, balance all reactants. Okay, make sure you have mole balance on either side, stoichiometric balance, for all reactants except for hydrogen and oxygen. Do not balance hydrogen and oxygen. And that is because our next two steps are how we are going to balance hydrogen and oxygen using our tools of water and H+. So our third step, after we've balanced all of our reactants, is to balance each half reaction for oxygen using water. Now we have to go in this order. You must follow this order. You can't go out of order, because the next step then has you balance each half reaction for hydrogen using H+'s. The reason we have to go in this order is because the addition of water adds even more hydrogens. Okay, so you're accounting for the addition of water by balancing in your next step by balancing for hydrogen using H+, which we'll see as we start to practice. But we have to balance for oxygen first using water, and then since water introduces hydrogens, we have to balance our half reactions for hydrogens using H+. So even though if we have a half reaction that has no hydrogen in it, and we have to balance for oxygen, we then have to do that fourth step to balance for hydrogen because the water introduces hydrogen there. Okay, so we have to follow these steps in order exactly as they say, or else you are not going to have a balanced chemical reaction at the very end. So once you've balanced your half reactions for oxygen and hydrogen, you then want to balance your half reactions for charge using electrons. So remember, we just write electron as E1 or E minus. We can add multiple of those electrons by writing 2E minus, 3E minus, 14E minus. You never know how many electrons you're going to need. Okay, so you want to balance each half reaction for charge. And again, that does not mean 0 on either side. It could also mean the same negative charge on either side or the same positive charge on either side. You're just going to use those electrons to do that. Okay, so once you've balanced each half reaction for charge using electrons, you then want to multiply the reactions to make the number of electrons equal. So if you used 1 electron in one half reaction and 2 electrons in the second half reaction, you would have to multiply the first reaction by 2 in order to make sure that the electrons are equal. Again, because Leo must equal Ger. The number of electrons lost must equal the number of electrons gained. Finally, once you've balanced your reactions for electrons and make those number of electrons equal, you're going to add those equations up and cancel any identical species. This will typically be electrons, hydrogens, or waters. Okay, you're probably those are the main things that you're going to have to cancel, is either going to be hydrogens, electrons, or waters. And then once you've added those up, just double check your balancing and make sure that your charge is balanced on either side. Your number of moles and molecules of each compound and element is the same on either side, because if it's not balanced, then you did one of your first 6 steps incorrectly. Okay, so let's start practicing with these steps. You are going to have to memorize these steps, so the best way to memorize these is to just practice, do a bunch of these practices, not only in this video, but also in your ALEX homework with your SI. Go to the review sessions and practice with them. They can help you there as well. So here, we want to balance the following using the half reaction method. So these 7 steps are the half reaction method. Okay, so we have a manganese with O4, MnO4 minus, reacting with iron 2 plus, creating Mn2 plus and iron 3 plus. So we can see that this is not easy to balance without the half reaction method because those oxygens just disappeared. Where did they go? We don't know. Okay, so we have to balance this using the half reaction method because it's not easy to balance these redox reactions using our typical balancing methods. So let's follow our steps. Our first step is to write the separate half reactions. So we have MnO4 turning into Mn2+, and Fe2+ turning into Fe3+. So we have MnO4 minus turning into Mn2+. I like to put these half reactions kind of in the middle of my page with a little bit of room on either side, because you're going to have to start adding hydrogens and waters and electrons and everything like that. So you need to have room to add those. It's not going to be a pre-balanced reaction. That's totally fine. When we add them up, that's when the whole thing gets pretty, okay? But just give yourself the room so that you're not missing out or losing any of your charges or your hydrogens or waters or anything when you're balancing. And then our second half reaction is Fe2+ turning into Fe3+. Okay, so that's our first step done. Woohoo. The second step says for each half reaction, balance all reactants except for hydrogen and oxygen. So let's see, I have manganese, there's only one and one manganese there, okay? We're not looking at charge yet, we're just looking at number of the elements. So my manganese is balanced, we're ignoring that oxygen, and my iron is balanced, okay? So it's balanced on either side. So we are good with balancing, we did our second step. Now we want to balance each half reaction for oxygen using H2O. So in our first half reaction, I have 4 oxygens on my reactant side, which means I have to add 4 waters to my product side. So now I have 4 oxygens here and 4 oxygens there. So oxygen is now balanced. So this is how we're using water to balance for oxygen. Okay, each water has 1 oxygen, so however many oxygens you need to balance out on the other side of the equation is how many waters you add. Okay, so now let's look at our second reaction. There are no oxygens, so we do not need to put in any waters to balance for oxygen. So we've done our third step. Now we want to balance each half reaction for hydrogen using H+. So when I introduced these 4 waters, yes, I got my oxygens to balance, but I also introduced 8 hydrogens on my product side. So now I have 8 hydrogens on my product side and 0 hydrogens on my reactant side. So I have to add 8 hydrogens, 8 H+'s on my reactant side to balance that out. So remember, when you're looking at water, water has 2 hydrogens in it. Each molecule has 2 hydrogens in it. So whatever the coefficient out in front is, you have to multiply it by 2, and that's how many hydrogens you would need to add. Our second reaction has no hydrogen, so we do not need to balance using hydrogen there. So that is our fourth step. Our fifth step is then balance each half reaction for charge using electrons. So what I like to do is take charge stock, or stock of my charge, where I highlight each side of each reaction so that I can, in a different color specifically, so I can see what the charge is on either side, so I know how many electrons to add. So my charge here is 8 plus and 1 minus, so this is then 7 plus. Okay, so I had 8 hydrogens with a plus charge. I then have 1 MnO4 with a minus charge, so 8 positive minus 1 is 7 positive. Okay, so just make sure you're double checking your charges there. And then on my product side, I have a total charge of 2 plus because water does not have a charge. So all that charge is coming from the Mn. In my other half reaction, I have a charge of 2 plus and a charge of 3 plus coming from each of those ions. Okay, so now that we've taken stock of what the charge is on either side, we can start adding electrons to balance it out. Okay, so if I have 7 plus on one side of my reaction and 2 plus on the other side of my reaction, and the only thing I can do is add electrons that will essentially subtract from that charge, how many electrons do you think I need to add, and onto what side do you think I need to add them in order to balance out the charge? Remembering that charge balance does not mean 0 on either side, it just means the same charge. We need to add electrons to our reactant side for this first reaction, because if I add 5 electrons, I'm essentially taking 7 plus and subtracting off 5, which gives me a charge of 2 plus, and 2 plus equals 2 plus. You cannot add electrons on either side of the reaction. It doesn't work like that. They can either go on one side or the other. Okay, so only add enough electrons so that your charges are balanced. Typically, you're going to add the electrons to the more positive side. And that's because we can only remove charge, we can only subtract from that positive charge. So in order to do that, you have to go from the more positive side. So for our second reaction, what side do you think I need to add the electrons to, and how many electrons do I need to add to get charge balance? Our electrons would go on the product side because it's the more positive side, and I only need to change this charge by 1, so I would only add 1 electron, because I would then subtract off 1 and get a 2 plus, and 2 plus equals 2 plus. So we've completed our 5th step. We balanced each half reaction for charge using our electrons. Our next step tells us that we need to multiply the reactions to make the electrons equal. Well, in my first reaction, I used 5 electrons, and in my second reaction, I used 1 electron. So I need to multiply this whole second reaction by 5 so that I get 5 electrons equaling 5 electrons. So that would end up being 5 iron, 5 electrons. So that is our 6th step. Our final step is to add our equations and cancel our identical species. So we are going to add these up. We have 5 electrons plus 8 hydrogens plus MnO4 minus plus 5 iron, 2 plus. So I just added up everything on this side of my arrows in both of those reactions. On the product side, I then have 5 iron, 3 plus, plus Mn2 plus 4 H2O, plus 5 electrons. It doesn't matter the order that you put these in, okay? You can put them in any order as long as they're on the right side, okay, and have the right coefficients out in front of them. Whatever order you choose is fine to put in. Okay, so we've added them up, and now we want to cancel our identical species. Well, we know there are going to be 5 electrons on this side and 5 electrons on that side. Our previous step accounted for that, so those electrons are going to cancel out. We then have 8 hydrogens. There's no hydrogens on the other side. We have an MnO4 minus, but there's no MnO4 minus on the other side. We have 5 iron, 2 pluses, but there's no 5 iron, 2 pluses on the other side. So everything is properly canceled. So our final equation that we would put in to our ALEKS homework is going to be the simplified version of this reaction. So all things canceled and everything like that. So if we were to type this in for our ALEKS homework, we would put 8H plus, MnO4 minus, 5 iron 2 plus, goes to 5 iron 3 plus, plus Mn2 plus 4 H2O. We can double check our balancing. We have, in terms of our coefficients, we have the right number of everything there. And then if we look at our charge, we have 8 plus, 10 plus, and a minus. So that is overall, this charge is going to be 8 plus minus 1 plus 10 plus. I guess we just put 10. So that's going to be 17 plus. And on this side, we have 15 plus 2. And that's 17 plus. So our charge is also balanced on either side. Again, this is showing that charge balance doesn't mean 0 on either side. It just means the same charge on either side. So let's practice another one of these. We have to start getting comfortable balancing these half reactions because they are going to be very useful for us in the remainder of this chapter. So we need to master it now so we can utilize it later. So in this problem, I'm only giving you one half reaction. So given only one half reaction, balance the reaction, I should say there's only one, and determine if it is the oxidation or reduction half reaction. So since we only have one half reaction, we get to skip the first step, we get to skip the fifth step, the sixth step, and the seventh step, because 5, 6, and 7 account for having 2 half reactions present. So when we're only given one half reaction, we only have to do steps 2 through 4. So I like to personally rewrite these half reactions again so that I can put them more center and have more room on either side of my product and reactant to account for everything that needs to be added. Okay, so our first step, so step number 2 here, is going to be for each half reaction, balance all reactants except for hydrogen and oxygen. Well, chromium is balanced with chromium. There's one of each, so we've done that step. So that's balanced. We're ignoring the oxygen because that's our next step, is to balance each half reaction for oxygen using H2O. So on my reactant side, I have 7 oxygens, therefore I need to add 7 waters to my product side. Okay, 7 oxygens on my reactant side leads to 7 oxygens on my product side because each water has 1 oxygen. So I've done step number 3. Next, we want to balance the half reaction for hydrogen using H+. Well, when I added my 7 waters, I also introduced 14 hydrogens, right? There's 2 hydrogens in each water molecule. If I add 7 water molecules, that's 14 hydrogen ions, okay? So I have to balance my 14 hydrogens on my product side by adding in 14 hydrogens to my reactant side. Okay, hopefully you're starting to see why we have to use these steps for these complex reactions, because it's not as simple to balance them with just stoichiometry and stuff that we learned in General Chemistry 1. There's this introduction of waters and these weird numbers of hydrogens that you would never think of to add in these chemical reactions if you were just asked to balance them the regular way. So we have to go through these steps. Oh, I have a typo. We don't ignore 5. We can only ignore 6. We have to do 5. We have to balance with electrons, sorry. Okay, I shouldn't have crossed out 5, sorry. So now that we've balanced our hydrogen with 14 hydrogens on our reactant side, we now have to balance the half reaction with electrons. So we've done our stoichiometry, we've balanced for our individual elements, now we have to do our charge balance. So let's take stock of what's on either side in terms of charge. So on our reactant side, we have 14 positive ions, and we have 1 2 minus ion. So we can rewrite that as 14 minus 2, right? Those 14 positives are then, we then remove 2 of them because of the 2 minus. So this gives us a charge of 12 plus on our reactant side. On our product side, the only thing that has a charge is the chromium, and that has a charge of 3 plus. So we have a charge of 12 plus on the reactant side and 3 plus on the product side. We now have to balance with electrons in order to get the same charge on either side. So remember, we have to add electrons to the more positive side. So which side do I need to add the electrons to, and how many electrons do I need to add? We need to add the electrons to the reactant side because that's the more positive. And we need to add 9 electrons because by adding in those 9 electrons, we subtract off 9 from that 12 plus and we get 3 plus. So we now have a 3 plus and a 3 plus, so we have charge balance. And that is our half reaction balanced using steps 2 through 5. 6 and 7 would require another reaction there. So the last part of this problem is to determine if this is an oxidation or reduction half reaction. So oxidation reactions would have the electrons in the product side, and reduction half reactions would have the electrons in the reactant side. So since our electrons are in the reactant side, we had to gain those electrons. This would be the reduction half reaction. Okay, let's try another one. I want you to pause your video and try this now on your own. Again, I'm giving you only one half reaction, so we can ignore step 1. Step 6 and step 7, we have to do steps 2 through 5. So given only one half reaction, balance the reaction and determine if it's the oxidation or reduction half reaction. So pause your video and try this one now. It's okay if you get stuck. Okay, if you get stuck, just come back to the video and work on it with me so that you can see where you went wrong and fix your mistakes. Because again, with these types of problems, it's all about practice, and it's all about, if you get stuck, figuring out where you went wrong and correcting that so that you can improve on your next problem. Okay, let's jump into this. So I'm going to rewrite this. NO goes to HNO2. So our first step is balance all of our reactants except for oxygen and hydrogen. Nitrogen is balanced on both sides, so we don't need to do anything, so check that. Balance each half reaction for oxygen using water. So we have 2 oxygens on our product side, but we also have 1 oxygen already on our product side. So we only need to add 1 water to our reactant side. So now I have 2 oxygens to balance out the 2 oxygens. So let me check that off. Now we want to balance the half reaction for hydrogen using H+. So on this side I have 2 hydrogens, and on our product side I have 1 hydrogen. So I need to add an additional hydrogen ion in order to balance that out. I now have 2 hydrogens. Okay, so just make sure, we haven't seen this in our examples just yet, so this is why we're showing it here, that if you have oxygen or hydrogen in your compound already and they're on either side, you have to account for that. So just make sure you're double checking your balancing as you go. So we've done our fourth step there. So we've balanced for hydrogen. We can always double check. I have, let's see, hydrogens, I have 2, oxygens, I have 2, nitrogens, I have 1. Here I have 2 hydrogens, I have 2 oxygens, and 1 nitrogen. Always double check. The best thing you can do before getting in these problems is to just make sure everything is balanced along the way, so that when you get to the very end, if we're doing a more complex problem where we're doing both half reactions, you don't get to the end and the whole thing's wrong. Okay, so just double check yourself as you go through. Okay, so our last step is to balance for charge. So let's take stock of what's on either side. On our reactant side, we have a charge of 0. Okay, that's an easy one. And on our product side, we have a charge of +1. So we want to add our electrons to our more positive side. So we would add 1 electron to our product side, because that will subtract 1 and give us a charge of 0. Therefore, we have an overall charge on both sides of 0, and that is our balanced half reaction. Since our electron is in the product side, this is then the oxidation half reaction, because oxidation electrons are lost. Okay, oil rig, oxidation is lost. Leo, lose electrons, oxidation. Since they are on the product side, this is the oxidation half reaction. Okay, so that was balancing our reactions in acidic solution. We saw in each of these examples that we have acidic written in parentheses to show us that it's in acidic solution. Just looking at the balanced equation, or the original equation that we're given, doesn't tell us if it's acidic or not, but we can see from our final equation that it is acidic, because all of our reactions that we've looked at so far have had H pluses in their final reaction, okay, whether that was the half reaction or the completed redox reaction. So we saw H pluses there, and we know that H plus means acidic. Now what we want to look at is, what if instead of acidic, we're given basic solutions? So as I said before when we were introducing this, when we have basic conditions or basic solutions that we're balancing these complex reactions in, we still follow our first 7 steps. So the first 7 steps that we see here are the same as what we saw before. Okay? We now just add 2 additional steps at the very end of that reaction. So our 8th step is now, for each hydrogen ion in the final equation, add 1 hydroxide ion to each side of the equation to make water. Okay, so if we have 1 hydrogen on one side, we would have to add OH to either side, to both sides, in order to make water and make it a basic solution. Okay, and then since we're making water from doing that, then our final step is to make any additional cancellations due to the new water molecules. Okay, so we just have to double check our canceling and simplifying from there. So let's just jump into a practice problem where we're going to practice those new steps. Again, just because it's easier to explain these when we have a practice problem right in front of us. So for this problem, we're still given only 1 half reaction, and we want to balance the reaction and determine if it's the oxidation or reduction half reaction. So I have OH minus turning into O2, and now I'm given that it's in basic solutions. So we're going to follow our steps exactly as we have it. Again, we don't need to do step 1 since we're only given 1 half reaction. We don't need to do step 6 or 7 because we don't need to add any equations up. So the first thing that we want to do, OH minus goes to O2, is we want to balance each half reaction for all reactants except hydrogen and oxygen. Well, our only reactants are hydrogen and oxygen here, so step 2 is done. Now we want to balance for oxygen using water. So on my reactant side, I have 1 oxygen. On my product side, I have 2. So I need to add 1 more water in there to balance out my oxygens. I now have 1, 2 oxygens to balance out the 2 oxygens. Okay, so we've done step 3. Now we want to balance each half reaction for hydrogen using H+. So on my reactant side, I have 3 hydrogens, and on my product side, I have none. So I need to add 3 hydrogen ions there in order to balance out my hydrogens. So I now have 2 oxygens on either side and 3 hydrogens on either side. So we are now balanced in our compounds and elements. Now we want to balance the half reaction for charge. So let's take stock of what our charge is on either side. On our reactant side, we have a -1. And on our product side, we have a 3+ coming from those 3 hydrogens. So what side do we need to add the electrons to, and how many electrons do we need to add? We add our electrons to the more positive side, and since our more positive side is 3+, we need to balance out to the -1, so we need to add 4 electrons to our product side. Okay, so that's going to subtract off 4 from that 3+ to give us a -1. -1 balances with -1. Okay, so just make sure you're double checking those charges, making sure you have charge balance on either side. So that is step 5. Now, in our previous examples, this is where we would stop. But because this is a basic solution, we have to do our 2 extra steps. So we can see here that we have 3 H+, and again, H+ means acidic, but we know this solution is basic. So essentially what we have to do is make water with, in order to show that this reaction is basic. So step 8 says, for each hydrogen ion in the final equation, add an OH- ion to each side of the equation to make water. So my product side has 3 H+. So for each of those H+, I have to add 3 OH-. Now whatever you do to one side, you must do to the other. I'll write that. So whatever you do or add to one side, you must do or add to the other. And I'm just going to put a disclaimer that that excludes electrons. Okay, because that's our step there. So because I added 3 OHs here, I need to also add 3 OHs here. So now we can change our equation here because 3 OH- and 3 H+ make 3 waters, right? H+ and OH- create 1 water. If there's 3 of them, we create 3 waters. So this then gives us a product side that looks like this. O2 plus 3 H2O plus 4 electrons. Now we can look at our reactant side. I had an OH here already. That's not always the case in these basic reactions, but since the OH was already there, we're going to add 3 more OHs, so we get 4 OH- and an H2O here. Okay, so that's our step 8. For each of those hydrogens, we added an OH ion to either side. Okay, whatever you add to one side, you add to the other in order to make water. And now we have an equation where I have an OH- here, and we know OH- means basic, and this is in basic solution. So a good way to remind yourself that you did the problem correctly and that you followed all of your steps is, if it says basic, I better have some OH- ions down there. Very rare cases do all the OH ends up canceling out. Okay, so just keep that in mind. There could be a time where the OHs don't actually show up, but remind yourself, if it's basic, I need to be adding some OHs because those are basic ions. Now our final step, so we did step 8, is to make any additional cancellations due to the new water molecules that we made. So I now have 3 waters on one side and 1 water on the other. So just like in math, if I had x on one side and 3x on the other, I could cancel them out. So one H2O is going to cancel with one of these H2Os, leaving me with 2 H2Os. Okay, I just subtracted that H2O out. So we have 4 OH minuses turning into O2 plus 2 H2O plus 4 electrons. And that is our balanced half reaction. Okay, we know it's a half reaction because there's still electrons present. If it was 2 reactions we were adding together, there would be no electrons present, but we didn't do that. So our final task is to determine if this is the oxidation or reduction half reaction. Well, our electrons are on the product side, meaning they were lost in the reaction. If they were lost, this means this is an oxidation. Oxidation is loss. So let's keep practicing. Now for this problem, we've already done steps 2 through 5. We did this in a previous slide. Here it is, what we did before when we were in acidic solutions. But now the problem says, well, now this is in basic solution. So we've done step 2, 3, 4, and 5. We now just need to do step 8 and 9. So let's just simplify or rewrite this equation out just so it's easier to see. So we have 9 electrons plus 14 hydrogens plus CrO7, 2 minus, goes to Cr3 plus 7 H2O. Okay, so that is our reaction in acidic solution. Again, we know that because of the H+. So now if we have it for basic solution, for each hydrogen ion in the final equation, add 1 OH ion to both sides. So I have 14 hydrogen ions on my product or reactant side, so I then need to add 14 OH minuses to both sides. Okay, so that's going to give us 9 electrons plus 14 waters plus CrO7, 2 minus, goes to Cr3 plus, sorry, typo, 3 plus 7 H2Os plus 14 OH minuses. Okay, so that's step 8. We added the OH minuses to both sides. Okay, I'm actually going to change that to red to show that we added them. Okay, and now our final step says to make any additional cancellations due to the new water molecules. So in my reaction, I now have 14 waters on one side and 7 waters on the other. So these 7 waters will cancel out with 7 of the waters on the other side, leaving me with 7 waters left over. So my final equation is 9 electrons plus 7 waters plus CrO7, 2 minus, goes to Cr3 plus 14 OH minuses. And we now know that this is basic because of those OH minuses that are left over. There's no more H pluses around because it is basic, not acidic. So now let's jump into a practice problem where we have to do both half reactions again. So we took a break from that when we started off. We looked at just the individual half reactions just to get our bearings on what those rules and guidelines are for balancing these. But now let's turn back to doing the 2 half reactions. So we have a redox and an oxidation half reaction. And using our steps that way to use all of the steps now. So we want to balance the following using the half reaction method, and we know that this reaction is in basic solution. So let's start this off. Our first step is to separate our two half reactions. So we can see that Cn minus is turning into CnO minus. That's one of our half reactions. And then we have Mn, I'm gonna move this up a little, MnO4 minus turning into MnO2. So we now want to make sure everything is balanced besides oxygen and hydrogen, which it is. Carbon and nitrogen are balanced, and the manganese are both balanced, so we are good there. Our second step is to balance for oxygen using water. So in our first half reaction, we have 1 oxygen on the product side, so we need to add 1 water on the reactant side. And then in our second half reaction, we have 4 oxygens on our reactant side and 2 oxygens on our product side, meaning we have to add 2 waters onto our product side to balance out those oxygens. So we now have 4 oxygens on either side there. So our oxygens are balanced. Our next step is to balance out hydrogens with H pluses. So in our first reaction, we have 2 hydrogens on our reactant side and none on our product side. So we need to add 2 hydrogens to our product. And for our second reaction, we have 4 hydrogens on our product side and none on our reactant side. So we need to add 4 hydrogens to our reactant side. So now we are all balanced in our number of atoms and molecules, and now we just have to balance for charge. So our next step is to use electrons and balance for charge. So let's take stock of what's on either side. In our first reaction, we have a -1 charge on our reactant side and a +1 charge on our product side. Remember, this -1 is going to cancel out one of those 2 pluses, so we have a +1 on our product side. And then in our second reaction, we have a 4+ and a minus, leading to a 3+ charge on our reactant side and a 0 charge on our product side. So if we want to add electrons, we always want to add them to our more positive side. So in our first reaction, that is going to be on our product side. So we're going to add 2 electrons in order to subtract off 2 and get a -1. So we have -1 and -1. So our charges are balanced there. And then for our second reaction, we're going to add our electrons to the reactant side, because that's the more positive side, and we are going to add 3 of those. So you can subtract off 3 and get a charge of 0. 0 and 0 are the same charge. Okay. Now that we have 2 reactions that we have to worry about, we have to go into our next step, which tells us that we have to multiply our 2 equations so that the number of electrons are equal. So our LEO and our GER have to equal each other. Well, in our first reaction, we had 2 electrons. In our second reaction, we had 3 electrons. So we need to multiply both of these equations, okay? Each equation can be multiplied by an individual number. They don't need to be the same number, okay? We need to multiply those so that the number of electrons is equal. So our first equation, we're going to want to multiply by 3 in order to get 6 electrons. And our second equation, we're going to multiply by 2 in order to get 6 electrons. So when you don't have a least common denominator between them, or you don't have to just multiply 1, just multiply them by the opposite, okay, just to make the same number. I'm going to rewrite these just so that there's no confusion in what I'm writing out. So I'm going to rewrite these now down here. So let's see, we have 3 H2Os plus 3 Cn minuses goes to 3 CnO minus plus 6 H pluses plus 6 electrons as our first reaction. In our second reaction, we have 6 electrons plus, let's see, 8 H pluses plus 2 MnO4 minuses going to 2 MnO2s and 4 H2Os. Okay, so we multiplied those two equations so that our number of electrons are the same. So we can see that these electrons are going to end up canceling with each other. And our next step is to then add up our two equations and simplify them by cancellation. So we have 3H2O plus 3Cn minus plus 8H plus 2MnO4 creates 3CnO minus plus 6H pluses plus 2MnO2s plus 4 H2Os. So looking at that combined equation, think about what would cancel. Well, we can see that these 3 waters will cancel out 3 of the 4 waters on that side, and these 6 H pluses will cancel out 6 of the 8 H pluses, leaving us with 2 H pluses on that side. So we'll just cancel that out, these are gone. Okay, now if this was an acidic solution, this is where we would stop. That would be our final balanced chemical equation, knowing that we had H pluses there and that this is an acidic solution. However, the problem states that this is a basic solution. So what we need to do is cancel out our H pluses by adding in the same number of OH minuses to both sides of the chemical equation. So because there's 2 H pluses, I'm going to add 2 OH minuses in order to create a side of 3Cn minus plus 2H2O plus 2MnO4. Now because I added 2 OH minuses to my reactant side, I also have to add them to my product side. So that would give me a product side of 3CnO minus plus 2MnO2 plus 1H2O plus 2 OH minuses. We can see here that we can simplify further to account for the additional waters. So this water is going to cancel out with one of these waters, leaving us with 1 water left over. And that is our final balanced chemical equation for this redox reaction. It's a lot. It is a lot of work there to go from this starting equation all the way down here for this basic solution. So we just gotta make sure we're following those steps all in order, making sure that everything is balanced and accounted for. And again, it just comes down to practice, practice, practice. We're going to do a lot more practice in this lecture, and you're going to do a lot of practice in your ALEKS homework. So let's do some more practice. Balance the following redox reaction using the half reaction method. So here we have Cr2O7 plus C2O4 creating Cr3 plus CO2, and this one is specifically in acidic conditions. So when you get to your homework, you're going to read the problem. It's either going to tell you that it's basic or acidic, or you're going to be given the total balanced chemical equation. You're either going to see an H plus or an OH minus, and that's what's going to tell you if it's acidic or basic, so you know which rules, which guidelines to follow, either the 7-step or the 9-step. So this one's acidic, so we only need our 7 steps. So what I want you to do is pause your video and try this problem independently. Okay, try it independently, try to get through as much of the problem as you can using those 7 steps and referencing back to our other practice problems. And then when you're either done or if you get stuck, come back to the video because we will do it together. Okay, I'm going to start going through these problems a little bit faster, just so that we can start getting into what's going on, what's happening. Feel free to pause the video and rewind it if you're missing something or if you're unclear on something. Feel free to just go back and take your time going through these problems with me. So our first step is to separate this into the two half reactions. So we have Cr2O7 turning into Cr3+, and we have C2O4, 2-, turning into CO2. Our first step is to balance everything but oxygen and hydrogen. So we need a 2 in front of our chromium and a 2 in front of our CO2 to balance out the chromium and the carbon on both reactant sides. Okay, we haven't had to do that in one of our practice problems yet, so this is the first one where we're seeing that. So hopefully we didn't miss that, because that's what's going to help us with our charges. Okay. So now that we've balanced for all of our reactants except oxygen and hydrogen, we're going to add water to balance out our oxygens. So in my first equation, I have 7 oxygens on my reactant side and none on my product. So we're going to add 7 waters to balance that out. In my second equation, I have 4 oxygens on my reactant side and 4 oxygens on my product side. Therefore, I do not need to balance with water in my second equation. Okay, our next step is to then balance with hydrogens. So we are going to add 14 hydrogens to my reactant side because my product side has 14 hydrogens that I added with water. In my second equation, there is no hydrogen, so I don't need to balance any hydrogens there. This would work if I wrote H+. There we go. H+. Perfect. So now that we have everything balanced stoichiometrically for our individual elements and compounds, we now need to balance for charge. So let's take stock of either side. In my first equation, I'm missing a 2- in my notation there. So I have a 14 plus and a 2- leading to a charge of 12 plus. And on my product side, I have 2 Cr3 pluses leading to a charge of 6 plus. In my second equation, my C2O4 just has a 2- charge, and my CO2 has a 0 charge overall. So now that we know where our charges are for each of these, we can now add our electrons to the more positive side. So in our first reaction, the electrons are going to be added to the reactant side. In order to balance out the 12 plus and the 6 plus, I need to add 6 electrons in order to get a 6 plus charge. It should be a -6 there. Okay, so now my charges are balanced. I have a 6 plus and a 6 plus. In my second equation, I'm going to add my 2 electrons to my product side to account for the 2- in my reactant side. So 0 minus 2 gives me a -2. So we have -2 and -2. Okay. So now that we have our charges balanced in our individual equations, we now have to multiply either one or both equations in order for the number of electrons to be the same. So I have 6 electrons and 2 electrons, meaning I can take this whole second equation and multiply it by 3. This would then give me, let's see, 3 C2O4, 6 CO2, and 6 electrons. Now that we've multiplied, we can now add these two equations together in our next step. So we know our 6 electrons are going to cancel on both sides, and this is going to leave us with 14 hydrogen plus Cr2O7, 2- plus 3 C2O4 going to 2 Cr3 plus 7 H2O plus 6 CO2. Okay, now we just double check and simplify. Nothing needs to cancel. I don't have waters on both sides. I don't have H pluses on both sides. So overall, I think we are good there. And that is going to be our final balanced equation. We do not have to do our last two steps because this is an acidic solution. Okay, and in our last practice problem here, we want to balance the following redox reaction using the half reaction method. This time we have a basic solution. So pause your video and try this problem independently using your rules for basic solution balancing, remembering that you should try to get through as much of the problem as you can until you get stuck or until you finish, and then come back to the video to check your work. Okay, our first step is to separate our two equations, our two half reactions. So we have NH3 going to N2H4, and then we have ClO minus going into Cl minus. So we need to double check that all of our reactants are balanced except for hydrogen and oxygen, meaning we need a 2 in front of our nitrogen, and other than that, everything else is balanced. So now we can move on to our next step of balancing for oxygen using water. In our first equation, we have no oxygen, so we don't need to add any waters. In our second equation, we have 1 oxygen on our reactant side and none on our product, so we need to add H2O onto our product side. Okay, our next step is to then balance for hydrogen using H+. So in our first reaction, we have 6 hydrogens, right? That 2 is going to apply to those hydrogens there. So we have 6 hydrogens on our reactant side and 4 on our product side. So we need to add an additional 2 hydrogens to our product side. In our second equation, we have 2 hydrogens in our product side and none on our reactant. So we need to add 2 hydrogens to our reactant side. And now we are completely balanced in terms of number of moles and molecules, so we can now look at charge. In our first one, we have a charge of 0 on our reactant side and a charge of 2+ on our product side. In our second reaction, we have a charge of, 2+ and a minus is 1+ on our reactant side and 1 minus on our product side. So we now want to add electrons to our more negative side or more positive side in order to balance out our charge. So in our first reaction, we're going to add 2 electrons to our product side. So we'll take 2+ minus 2 gives me 0. That's a charge of 0 on both sides. And then for our second equation, we're going to add 2 electrons to our product side. 1+ minus 2 is equal to -1. -1 equals -1. Okay, so we're now balanced for charge. Since we now have 2 equations to look at, a redox or a oxidation and a reduction half reaction, our next step tells us to multiply either equation in order for the electrons to be equal to each other. Well, each equation utilized 2 electrons, so we do not need to multiply either of them. So we can move on to our next step where we add up our 2 equations together. So we know that our 2 equations, the electrons are going to cancel. We already know that. So we then get 2H plus ClO minus plus 2NH3 goes to N2H4 plus 2H pluses plus Cl minus plus H2O. Now that we have this, we want to simplify both sides and make sure that if anything is the same on both sides, they get canceled. So we actually have two hydrogens that are going to cancel out on both sides, and I think that's it for what we'll cancel. Okay, so we've canceled things. Now we have to worry about the fact that this is a basic solution. If it's basic, then for every H plus that's still present in the reaction, we have to add an OH minus to both sides. Well, as we saw, we just canceled out both of those hydrogens. They're both gone on both sides, so there are no H pluses on either side. Therefore, this is our final balanced chemical reaction for this redox reaction in basic solution. If we were to do it in acidic solution, it would look exactly the same. Okay, so as I said before, there are some cases where there won't be any hydrogens left in order for the OHs to add to, or the OHs will end up canceling out. Okay, it'll look exactly the same whether it was acidic or basic. Our last two problems are there for you to practice independently. So we have an acidic and a basic solution there for you. So what I want you to do is, before you move on to your next lesson, complete these two reactions and balance them using the half reaction method. The answer will be posted on e-learning for you to double check your work or double check your final answer. However, in order for this to be graded and for you to receive a grade for this portion of the assignment in your note pack, you have to show your work that you used and that got you to the final answer. So the final answer will be posted for you to check, but the work will not be shown. You have to show me the work. So it's there to double check your answer, and if you don't get that, you need to redo the problem.